Kia ora, team. I hope you're all doing okay. Hopefully the sound is coming through all goods. So let me know if that's happening in the chat. So our goal for today is to cover some stuff on refraction and lenses. Now you might not have heard of refraction before, but by the end of this, hopefully you'll be feeling comfortable. This again is designed to go alongside the slides, so we'll be working through that together. And then if you have any questions, you're welcome to fire them in the chat, and either your mates can answer them or I can come in and try and answer them, or alternatively you can save those questions and we can answer them when we have our Google Meet later this week. We'll also be talking about lenses, which are used all over the place. I've got some on my face right now, so we'll be talking about all these sorts of things today. So, as with all of the instructions each week, these slides are designed to be done on them, so you can hand them in at the end of the week as an assignment, and there'll be a little extra for experts things as we go. Additionally, there is an Education Perfect task for this week, which I think I set. If I didn't set it, then you're Education Perfect free for this week, which is nice, but I think I set one. So, Tarataki Duki is covering refraction, covering lenses, and covering ways in which lenses can be used. The last lesson will be just a summary of the content for the week. Okay, let's dive into refraction, and you can ask any questions as we are going through. All right, so the first thing here is you might have noticed this effect. It's the same effect that we see in the thumbnail, where the spoon doesn't line up with where it enters the water. And you probably want to have a little bit of a think of an explanation. Now you can have a go at this if you want to. You can write your answer in the chat or you can write it down on a piece of paper. If you want to, you can pause the video where we are right now and then see if you get it right. And I'll reveal the answer shortly. In 3, 2, 1. Okay, and the answer is due to this phenomenon called refraction, which we're going to learn about today. Now the reason why this is because light, as it travels through a substance, or it goes through a barrier, so into the glass and then to the water, there is a difference in essentially how dense the water is, and therefore how fast light can travel. And essentially what that means is that light bends as it enters those substances, which is kind of funky. And because light is bending, that changes the path that the light has to take to reach our eyes and gives this optical illusion that there is this difference in space between where the spoon is entering the water and when it actually ends up. Now this phenomenon is called refraction. It's explained really well in this short video here. So I encourage you, as like the first thing to do at the end of this, is to have a little bit of a go at watching this video, because if you're not getting it from either my explanations or the explanations of the slides, I think this video will be a great deal of help to you. So let's break down what this is. So refraction is kind of funky. We talked about how the incident ray comes in and it might reflect off a surface, right? If the light ray is able to pass through the surface, say into some water, we'll see a phenomenon called refraction. This happens because the water is more what we call optically dense. It's just dense. It slows down how quickly the water can move. And you'd expect that this incident ray would keep going in the exact same direction, continuing in a straight line. But that's not what we see. We see that the ray is bent, and it's bent towards the normal. So therefore, the incident ray is actually a larger angle than the refracted ray. The refracted ray is smaller because it's been bent towards. And that's kind of explained here in this little diagram, and you can see that as you go from one substance that allows light to pass through it to another substance, if they're different densities, then the light ray will bend. It's also true that how much the light ray bends is determined by the difference in how dense these substances are. So going from air to water is quite a big change. So you see quite a big bend, right? But some substances bend more than that. Some substances bend less when coming from air into that substance. And you can see that sort of shown there. So given that you know this information, you should be able to answer the question on this slide, right? Only one of these diagrams is correct. Now, I'm going to reveal this in a second, right? And this, by the way, this plastic block is plastic, but it's like see-through plastic, like maybe an old school milk bottle, something like that, or maybe like a plastic glass, something like that. You can imagine like a glass, just it was a big chunk of that kind of plastic, that see-through plastic. So I'll give you 10 seconds to figure this one out. You're welcome to fire up your answer as to which one of these you think is correct. Only one of them is correct. So you can type your answer as 1, 2, 3, or 4 in the chat. All right. I want to see some answers coming through. So make your guess now. And just while you're making your guesses, I'll be vamping for time. I want you to take a note of the different rays that are there. Have a look at the angles, have a look at some of the labels. Okay, I'll give you another couple of seconds to pop in your answer, right? Only one of these diagrams is a correct example of refraction. Okay. And I'm going to reveal the answer. Okay. In 3, 2, 1. The correct answer is 3. Now let's break down why. So, first things first. You've got the first example, you've got air and then the plastic block. And you notice the incident ray keeps going in the exact same direction. That's not what we would see with refraction. I told you before, refraction is where the light bends towards the normal, right? The second example is a good example of reflection, right? But you'll see this ray is labeled the refracted ray. That's not what it is. That's the reflected ray. It's a little bit of a different thing. We learned about reflection last week, didn't we? If we go to number 3 and 4, you both see that they've correctly shown that the second ray, this ray down here, is bending in towards the normal, right? What's wrong here is the labels. So you'll see that here we've got the incident ray, the one that comes in, and the refracted ray is the one that goes through the plastic block. And number 4, those are flipped, and we know that that's wrong. The incident ray is the one that comes towards the surface, and the refracted is the one that gets bent when it's inside the surface. So that is why number 3 is the correct ray. You can also see that on this one, the labels for those angles are also incorrect. So the angle that is refracted is up here when it really should be, as it's shown down on number 3, down at the bottom. So hopefully that makes sense. Thank you all for playing with that one. All right. Next thing up. This is a little bit of a demonstration of this exact phenomenon. So your job is to draw a little diagram in your book, and you can upload this to the slides here if you'd like to. And you can watch this. Now, if we were actually in class, we'd have you play around with these, and when we're back in class later on in the year, we will try and get these out and have a bit of a play. But what you'll notice is that the light does bend, in fact, as it goes through these plastic blocks, and we'll be able to see that here. Now, total internal reflection, for those of you who are keen for Extra for Experts, are interesting effects that you start to see where the light rays get trapped basically inside the block, and they don't have an easy ability to escape. And that's because of the angle that the light bends at. If you're interested in that, you can Google total internal reflection and learn a little bit extra if you're keen on that sort of thing. Now, we've understood these with like flat planes. When we start to introduce concave and convex lenses, right, just the same as we had concave and convex mirrors, we start seeing some funky things. So your job is to draw a diagram of what happens when 3 rays of light pass through a concave lens and what happens when 3 rays of light pass through a convex lens. Remember, last week we learned concave bends in like a cave, right? And convex flexes out, right? So we want you to draw those little diagrams. You can upload those photos to this. Now that we've done that, you should be able to have a go at explaining why things look kind of broken or bent when you see them entering water like this. And this video does a good job of explaining that. And our last little task for the week will be for you to, or for this lesson, will be to take photographs of your drawings so you can add them in. Alternatively, you could find an image that demonstrates these and then briefly explain it. There's also some extra facts if you're interested in reading, and you see here is a slide for you to place these things. Now comes the challenge. We've gone through this explanation, so hopefully, if you wanted to, if you're watching this at a later stage, you could pause this and explain to somebody how this image is formed. That might be a fun thing to do with your whānau later today. You could say to them, look at this person, and then you could explain to them exactly how this dude is able to look like he's holding up his own head, which is kind of funky. So I'll leave that with you. There's also some answers to those SciPad pages and a little extra for experts magic trick for you to have a little bit of a look at. All right, now we're moving on to our second lesson today, which is on lenses. So we've kind of talked about lenses already. We've talked about the phenomenon associated with them. But hopefully you can see that when you hold up a magnifying glass, things appear to be larger than they previously were. That's what we mean by magnification, right? Now, magnifying glasses are convex lenses, right? So they converge light together. And if you link that to what we just learned in the previous lesson about the way light travels, hopefully that helps to explain things, that you have these three rays of light kind of get bent in a slightly different way that helps us to view these things in this way. So I'll leave that for you to figure out in terms of an explanation. But all lenses are transparent materials which refract light and allow us to focus that light to a particular place, right? Now, the difference between a lens and a prism is that prisms don't focus the light, whereas lenses do. Lenses allow us to theoretically get it to a real point out in the real world, or an imaginary point that exists behind or in front of the lens, which is kind of funky. So we've talked about convex and concave. You get what these are. Now, if we had these in the classroom, you could have a little bit of a play around. You might have access to some at home. Some of you might even have these on your face right now. But convex lenses allow light rays to converge things together, which makes things look larger. So magnifying glasses are convex lenses. Concave lenses make things look smaller when we view through them. So yeah, convex lenses, objects appear larger. Concave lenses make them appear smaller. You'll notice that both of these lenses have the prefix bi on them. I'm going to give you the answer to this one. It's because they have that on both sides, right? You've got a side which is bulging out and another side which is bulging out in the case of the converging lens or the convex lens. Diverging or concave lenses are biconcave if they've got both sides like that. Cool. Bill Nye does a good job of summarizing this. So again, if you're feeling a little bit uncomfortable with the concept or you want another explanation, you can watch this great video from him. Now, your job for this week, to summarize this, is to use these information in these videos and in these slides to explain this table. That's all you need to do, fill out that table, right? So give that a go. There's also a couple of extra videos there for you if you would like. All right, now we're moving on to lesson 3, which is on refraction, right? So we've talked about types of lenses, we've talked about all these various things. Now we're on to refraction. The first thing for you to do is to looking at the differences between eyes and cameras. And that video does a good job of talking to us about how basically eyes and cameras do very similar things. They take in an image and flip it upside down onto a sensor. In the case of a camera, that sensor is electronic. Um, in the case of our eye, it's a little series of cells that respond to light. Both of these images are real, right? Because they're really projected in a real place. Um, and it's quite funky actually that we have eyes that allow us to change this automatically, which is quite cool, by changing the shape of the lens of our eye, as well as changing how much light we let in. Um, Now, this lesson, as much as it's about refraction, is also about applications of lenses. Because actually the previous lesson was on refraction. I think we mislabeled these, but that's okay. So lenses have a variety of uses. Um, there's kind of a bunch of obvious ones, right? And then there's some ones we use every day as well. But you will absolutely have encountered these and be encountering them around your home. You could even have a little bit of a go around your home and see what types of lenses you have available. We've put some detail in here for you to have an opportunity to read about how telescopes actually work and how they use lenses to allow us to be able to see things that are really far away. Now, most telescopes used to be you had to look through them with your own eyes. Many of them nowadays, they put them onto an electronic sensor so that you can record images. It's really funky. Like, I love telescopes. Now, we've got some answers to the SciPad page that this relates to in here, so you can look at those. But your final job for this week is to, or at least for this lesson, is to summarize your understanding of the applications of lenses. And you can pick any of them, and all you need to do is describe how the lens allows objects to appear in it. That could be describing how a camera works, could be describing how a telescope works, could be describing how glasses work, if you would like to do that instead, or a microscope, whatever you may want to pick. Just pop your explanation in there, and if you want, you can watch that video and that will help you out as well. There's some more extra for experts material in here, which explains his lenses in more detail if you need that. Now, our final lesson for this week is we are going to do this next week, the ray diagrams in human sight, but our lesson will be done over Google Meet. But we do have some summary questions for you, right? And these are key definitions that you need to be able to know in order to not just do well in the test, but ultimately understand the stuff we're talking about. So it's kind of a summary task. So you need to describe or define those terms in that list. If there's any that you're not sure, I'm happy to go through them when we have our Google Meet later this week. There's also a couple more extra for experts, which I think are really cool, on use of lenses in movie making and use of them in the manufacturing of big telescopes and things, which I think is really, really cool. All right, but that brings us to the end of the content for this week. So all I've got left to say is that I hope you're all doing okay. I hope you're looking after yourselves. If you have any partai, I'll stay on for a couple of minutes to answer any questions. Otherwise, you can review this at your own pace, and I'll see you later this week for our Google Meet. All right. Have a lovely rest of your day, team. I'll catch you all later.